Hello there, welcome to today's chemistry video. This video is about Chapter 1, the particulate nature of matter, covering the kinetic theory, Brownian motion, diffusion, and gas pressure. Just to note that it is in accordance with Cambridge IGCSE Chemistry syllabus, but it is pretty much the general fundamentals of chemistry. So let's get started. The first concept that we have to keep in mind is that all matters are made of particles. Your books, water, phones, and even us, they're all made of billions of small particles. Next, we have some terms to learn that will be used in the upcoming chapters. The smallest particles that cannot be further broken down by any chemical or physical means are called atoms. It only represents one type of an element. Then when these atoms join together, a new particle is formed, and we refer to them as molecules. It is a mixture of same or different types of atoms. Lastly, we have ions, which represent atoms or molecules that carry either a positive or a negative charge. We have three different states of matter: solids, liquids, and gases. We'll take a look at its distinguishing properties that are obvious enough for us to notice by just looking at them. Firstly, all solids have a fixed shape and a fixed volume. No matter where we place them, they will maintain their original shape and volume and will not flow even if they do not have a container around them. Next, we have a liquid. For liquids, their shape changes easily and will take the shape of the container, which means their shape depends on the place they rest on. They will flow easily, unlike solids. Gases have very different properties compared to solids and liquids. They have no fixed shape nor fixed volume. They will not take the shape of the container, and it is impossible to keep them in a fixed position. Another thing to note is their mass. They're much lighter than solids and liquids. Now let's study the difference in structures of solids, liquids, and gases. A solid is always arranged in a shape called a lattice. This picture here shows what a lattice looks like. They are able to stay in this position as there are strong forces between the particles. Furthermore, they do not move around but only vibrate in a fixed position. On the other hand, a liquid will not be in a lattice. The particles are still close together, but there are weaker forces of attraction between the liquid particles, resulting in a loose shape compared to a solid. This also allows the particles to move about slightly and slide past each other. A gas will again have completely different properties. Its particles are very far apart compared to a solid and a liquid, and this is due to having almost no forces of attraction holding them together. They're free to move about very quickly and are likely to collide with each other or with the wall of the container and bounce off in all directions, causing them to spread out. Changes of state. All substances are allowed to change its state under different temperatures. Starting from a solid, it can be changed to a liquid by a process called melting. Think of an ice under the hot sun. You'll see that it has turned to water within a second. As long as the temperature is higher than 0 degrees Celsius, it will immediately start to melt, and this temperature is called the melting point. What if we want to change it back from a liquid to a solid? We can simply freeze it back by lowering the temperature to below 0 degrees Celsius. Another name for this temperature is water's freezing point. A liquid can be changed to a gas by increasing the temperature. In the case of water, if the temperature goes above 100 degrees Celsius, it will be changed to water vapor. This process is named as boiling, and its temperature is the boiling point of water. An interesting feature about a liquid is that, instead of having to increase its temperature, some of its particles will be turned to gas. This is evaporation. Evaporation occurs at any temperature, and it is also a process where a liquid changes to a gas. For a gas to become a liquid, condensation needs to occur. If the temperature goes below 100 degrees Celsius, particles will form a liquid again. Sometimes, a solid can be changed directly to gas by sublimation. This is only observed in certain substances such as carbon dioxide, we call it as a dry ice, and naphthalene, a mothball that gives out gas that is used as a chemical pesticide or a deodorant, and iodine crystals that can be seen in our chemistry labs that give off purple fumes. Next, we have something called a heating curve. This curve can be drawn for any substances that go through a change of state from a solid to a liquid to a gas. At its lowest temperature, the substance remains as a solid and is warmed up as the temperature rises. Once it reaches a melting or freezing point, change of state occurs. Solid will change to liquid, and we can see that the graph is horizontal as the temperature does not change at this moment. Heat is used up to change its state, so the temperature remains constant. After completely changing to the liquid state, when temperature increases, it is again warmed up. At this part of the graph, evaporation occurs as well, since evaporation of a liquid occurs at all temperatures. When the temperature has reached its boiling point, liquid is turned to gas and the graph drawn will be horizontal until it is completely changed to gas. The substance now in a gas state will just get hotter when the temperature rises. Lastly, we have something similar here, a cooling curve. You can think of it as opposite to the heating curve. It starts from the highest temperature as a gas. As temperature decreases, gas is cooled. When it reaches the boiling point, gas is changed to liquid and the temperature will remain constant. Then when temperature is further reduced, liquid is cooled until it reaches the freezing point. Liquid will then be turned to solid by freezing and there will be no temperature change. After this point, the solid will just get cooler without any change in state. What we have covered so far sums up and explains the kinetic theory. Here's a list of points that define kinetic theory. A substance can be a solid, a liquid, or a gas and change from one state to another. For example, from a liquid to a gas. It has different characteristics in each state. For example, solids do not flow. The differences are due to the way its particles are arranged and move in each state. For example, gas particles are far apart from one another. So now that we have learned the kinetic theory, we can explain the change of state in terms of it. Here's the basic idea of why substances change their state. When there is a temperature change, its particles will take in or lose heat energy, and this will cause them to change their movement, arrangement, and the bonds formed between them. Since there are different forces of attraction present between the bonds, each substance will require different amount of heat to change its state. Let's learn the change of state again, this time in terms of kinetic theory. Firstly, melting. When a solid substance is heated, this heat will be transferred to its particles and will cause them to vibrate more. This will cause the solid to expand, and once it reaches its melting point, the particles will break away and form a liquid. How about boiling? A similar thing occurs. When a liquid substance gains heat, its particles will move faster as they will be supplied with more energy, and this will result in higher rates of collisions between the particles. Liquid will then expand, and at its boiling point, the particles will overcome the forces of attraction that were holding them and become a gas. Thirdly, evaporation. One important thing to note is that evaporation occurs at all temperatures, even at below boiling points. This is possible as some particles generally have more energy than the others, and have the energy to break through the bonds and escape from the surface of the liquid. Next, we have condensation and freezing. These processes are the opposite of boiling and melting, and at this time, energy is lost from the particles. Once the particles lose their energy, they will move more slowly, and even if there are collisions between the particles, they will not have energy to bounce away from each other. As the particles stay close, bonds will be formed between them and either become a liquid or a solid on further cooling. The diagram below shows the summary of all the processes. We have come to the second part of our video, Brownian motion. Let's first talk about its background before we move on to the theory. In 1827, a botanist called Robert Brown was observing pollen grains from a flower inside a beaker of water. Then he noticed that the pollen grains were moving even though they were not even alive. He could not find out the reason why, but 78 years later, Albert Einstein found out that it was because the water particles around them were constantly moving around and colliding with the pollen grains. So, by definition, it's random motion of particles suspended in liquid or a gas. It occurs because the particles are continually bombarded by molecules. It applies not only to water particles, but to all substances. And this was named after the first person who found it, Robert Brown. Now, take a look at the evidences of this special motion. Firstly, when we cook something, the smell spreads across the room over time. This is because the particles that cause the smell are bombarded by air particles, causing them to spread. Some evidence can be found in our own rooms. Under sunlight, we often see dust dancing in the air. What is making them dance? The dust particles are in fact being bombarded by the moving air particles. Moving on, we can find some evidence in science labs. When a crystal of potassium manganate 7 is placed in a beaker of water, we can observe that the purple color is spread in the water. Its particles have actually dissolved and mixed among the water particles due to Brownian motion. The same thing applies for gases too. Place a few drops of red-brown bromine in a gas jar and you'll notice the brown color spreading upwards. The movement of air particles will cause the bromine vapor particles to spread. Here comes the third part, diffusion. This is a simple process where particles will mix with each other by colliding with each other as they are constantly moving and bouncing off in all directions. The diagram here shows what it looks like. There are two factors affecting the rate of diffusion of gases. The first one is the mass of the particles. Given a cotton wool that gives off ammonia gas and another cotton wool that gives off hydrochloric acid gas, each placed in opposite ends of a closed tube, you'll notice that the white smoke, the product of these two gases, is formed closer to the cotton wool that gives off hydrochloric acid gas. Why is this so? This is because ammonia gas particles are lighter than hydrochloric acid gas particles and have traveled faster. We can conclude that the lower its relative molecular mass, the faster the gas will diffuse. The second factor is the temperature. We have learned that once the temperature is increased, gas particles will gain more energy and move faster. These particles will then have more ability to bounce further away and as a result dissolve faster. The higher the temperature, the faster a gas will diffuse. We've come to the final part of our lesson, gas pressure. All gases exert pressure as they are constantly bumping into one another. Let's see what happens to this pressure when temperature is increased. When gas is heated, the particles will take in more energy and move faster and faster. There will be more collisions, causing the pressure to increase. What about when a gas is put in a smaller space? Gas, unlike liquids and solids, can be compressed as they have space between the particles. Once compressed, these particles will have higher chance of colliding with the wall, again causing the pressure to increase. This does not apply to liquids and solids as their particles are already very close together and cannot be compressed. That is all for this video. Thank you so much for watching. I hope this has been helpful and a time-worthy lesson. For our next video, I'll discuss about the experimental techniques on measurement and method of purification. Please subscribe and like if you like to see more videos like this, and feel free to comment below your thoughts or any doubts. Stay safe and God bless you guys. Thank you and see you in my next video. Bye!